Hello! We will look at an example of mixed Nash equilibrium in the voting game. We start with the paradox of voting, or Down's paradox. The question that game theorists considered was, why do people vote? Voting has its costs. They could be time, cost of travel, bad weather, waiting in line, and in some countries, facing harassment for voting. So what is the benefit of voting? With a large population, the probability that one vote is the decisive vote is vanishingly small, so it is unlikely to matter anyway. So, the costs outweigh the benefits. From a selfish point of view, the expectation is that people don't vote. Of course, we see that in reality, people do vote. Voter turnout tends to be more than half and closer to 70% in major elections. Lots of research has been done to try to model this and explain why this is true. Generally, more people tend to vote if there is a close election, and there tend to be two frontrunners that get most of the votes. For us, we will model voter participation in the following way. Suppose there are two candidates A and B, and the number of supporters are A and B respectively. Without loss of generality, we will assume that A is at least B. Now each person has two choices. They can choose to vote or abstain. If they vote, then they incur a cost of C, where C is between 0 and 1. Regardless of voting or abstaining, each person gets a payoff of 2 if their supporting candidate wins, 1 for a tie, and 0 for a loss. We will start by looking at a pure Nash equilibrium. Suppose that A and B are both 1, so each candidate has exactly one supporter. Then we can write their payoff table like this. If both of them abstain, then there is a tie, so each of them get utility 1. If both of them vote, then there is still a tie, and both of them get utility 1 minus C. If one votes and the other abstains, then the player who votes gets utility 2 minus C because their candidate wins, and the other player gets 0. Now this payoff table might look a little bit familiar to you, as it has a similar setup to Prisoner's Dilemma. If both players vote, they get lower utility than if both players abstain. So voting is like stealing here. Let's look at a larger example where we suppose that A is still equal to B, but now they are both at least 2. We look at 4 different cases. Everyone votes. Not everyone votes, but there is a tie. One candidate wins by 1 vote, and one candidate wins by at least 2 votes. Are any of these cases pure Nash equilibria? In the first case, suppose that everyone votes. Then there is a tie and everyone has utility 1 minus C. If anyone decides to switch and abstain, then their candidate loses and they will get utility 0. So there is no incentive for switching, so this is a Nash equilibrium. In the second case, suppose that not everyone votes and there is a tie. Then one who abstains can decide to vote, which will make their candidate the winning one. So their utility changes from 1 to 2 minus C, which is a better one. So this is not a Nash equilibrium. In the third case, suppose that one candidate wins by 1 vote. Then one who abstains for the losing candidate can vote, which will result in a tie. So their utility goes from 0 to 1 minus C, which is greater than 0. And this is not a Nash equilibrium. In the last case, if one candidate wins by at least 2 votes, then one who votes for the winning candidate can decide to abstain, and their candidate will still win. So their utility will go from 2 minus c to 2. And this is also not a Nash equilibrium. So the only Nash equilibrium is when everybody votes. From here, we can conclude that in a close election, we expect more people to vote, which is quite intuitive. As an exercise, show that when A is strictly greater than B, there is no pure Nash equilibrium. Now let's move on to mixed Nash equilibrium. There are actually many mixed Nash equilibria, but they are not easy to find. We will discuss one possible scenario for a mixed Nash equilibrium, which has a counterintuitive result. Suppose that A is greater than B, and among all the A supporters, B of them will vote and A minus B of them will abstain. They are playing pure strategies in this case. Now suppose that every B supporter will vote with the same probability P. So the best that candidate B can do is a tie. It is easy to check that when P is equal to 0 or 1, this is not a Nash equilibrium. So we assume that P is strictly between 0 and 1. And we want to see which values of P could possibly be an equilibrium. We consider one supporter of B. We want to calculate the expected utility for playing vote and playing abstain as pure strategies. If they abstain, then B cannot win. So the utility of abstain as a pure strategy is 0. On the other hand, if they vote, then there are two possible outcomes. B ties with A only if all the other B supporters vote, which will give us utility 1 minus C. Otherwise, B loses and our utility is minus C. So the expected utility of vote as a pure strategy is P to the B minus 1 times 1 minus C, where the first part is the probability that the remaining B minus 1 voters all vote, and the second part is the utility of a tie, plus 1 minus P to the B minus 1 times minus C. The first part is the probability that not all of the remaining B minus 1 voters will vote, and the second part is the utility of a loss. And this is equal to P to the B minus 1 minus C. Now we are looking for a mixed Nash equilibrium. So when is it possible that this is a Nash equilibrium? What can we say about these two utilities? Well, we know that P is strictly between 0 and 1, so both strategies have positive probabilities. To be in the best response, support characterization implies that the two utilities are equal. So we have 0 is equal to P to the B minus 1 minus C, or P is equal to C to the 1 over B minus 1. So this probability gives us the best response from the B supporters to the actions of the A supporters. Given this P, we still need to check whether or not the A supporters are incentivized to change their mixed strategies. Currently, all of them are playing pure strategies. In order to switch, the utility of switching to the other pure strategy must be greater. So let's look at the two cases here. We first consider an A supporter who abstained. Their expected utility when abstaining is P to the B times 1, which is what happens when there is a tie, plus 1 minus P to the B times 2, which is what happens when A wins. And this is equal to 2 minus p to the b. And the expected utility for voting is 2 minus c. That is because if they change from abstaining to voting, then A is guaranteed to win. So 2 minus c is equal to 2 minus p to the b minus 1, which is less than or equal to 2 minus p to the b, since p is between 0 and 1. So switching to a pure strategy does not increase utility. So switching to any mixed strategy does not increase utility. There is no reason to switch. Now let's consider an A supporter who voted. Can you calculate their expected utility for voting? Their expected utility is p to the b times 1 minus c in the case of a tie, plus 1 minus p to the b times 2 minus c in the case of a win for A. This is equal to 2 minus p to the b minus c. And now suppose they decide to abstain. Then the number of A supporters who voted is b minus 1. There are 3 possible cases. Either A loses if all the B supporters vote, A ties if B minus 1 B supporters vote and 1 abstains, or A wins in the other cases. So now, can you calculate the utility for abstaining? The utility for abstaining is p to the b times 0 in the first case of a loss for A, plus b times p to the b minus 1 times 1 minus p times 1. This is for the case when there is a tie. The probability is calculated from the probability that b minus 1 votes, 1 abstains, and the number of choices of who abstains, plus 1 minus p to the b minus b times p to the b minus 1 times 1 minus p times 2, where the first part is the remaining probability. This is equal to this expression here. And you can use arithmetic to check that the expected utility for voting is at least the expected utility for abstaining. So there is no reason to switch here either. So now we can conclude that when p is equal to c to the 1 over b minus 1, this is a mixed Nash equilibrium. So now here is a question. What happens to the voter participation as cost increases? Well, we see that p is equal to c to the 1 over b minus 1. So if c increases, then p also increases. So more voters will vote. And that is quite unintuitive, but it is the nature of this mixed Nash equilibrium. So that is the voting game. In the next lecture, we will look at a special class of strategic games where a mixed Nash equilibrium is easily calculated. And this is a class of two-player zero-sum games.